Hello. Today, I want to talk more about systems of first order ODEs. And in particular, I'm going to help you with problems 5 through 7 on this current web work set. And it's all related to this fact I've written in blue. Every second order ODE, like this one here, y double prime is some function of y prime, and t. Every second order ODE can be written as a system of two first order ODEs. All right, and just I want to mention the picture today. You've seen this before. This is Half Dome in Yosemite Valley. It's a famous photograph by Ansel Adams. Okay, and I got this myself when I was in Venice, and I've been to Half Dome. I've climbed not up the front, but I've hiked to the top of there from the back the easy way, and I've been to Yosemite several times. Okay. All right. So let's talk about, just kind of show this fact, okay? If I have a second order ODE, and I'm assuming I can solve it for y double prime, it might have, I could have a y double prime squared, I might be in trouble. But I can solve for y double prime as a function of y prime and t. Then what I can do, if this is the thing, if this is true about the unknown function yt, I can write this as y prime equals v, and v prime is f of y. Well, I can't put y prime because the right-hand side can only depend on y and v and t, so that's a v, and this is a t. Okay? All right. Kind of enough said about that. Okay. So let me just remind you that the unknown function here is y of t. And here I have an unknown pair of functions, pair of unknown functions. Y of t and v of t, which is y prime of t. Now the reason we use v is because if y is position, then v is velocity, right? If y is position as a function of time, then v is the velocity function. Okay. Let's do an example. If we have y double prime equals minus y, all right, then, well, first, we'll just go and do it. I can write this as y prime is v, v prime is minus y. Okay? Let's think a little bit about a picture that goes with it as well. So if I have y double prime equals minus y, this has the general solution. Y is c1 cos t plus c2 sine t, which I might like to write often is y is r cos of t minus delta. Okay? So one of the things about this that's maybe not so good is if I plot y versus t, here's a solution. Here's 2 pi. Here's another solution, if I can do it right. Okay, this is like, maybe that's cos t. This would be a half times sine t. And one of the problems about this is that the solutions to this differential equation, if I draw them as y as a function of t, they cross each other, okay? They're all like a shifted cosine with different amplitude and maybe a phase shift delta, but You notice that we haven't really done a lot of drawing the pictures for y versus t. And this is kind of part of the reason why. I can start off with any position in any velocity, and I get a solution that goes through there, and they all kind of make a mess. Whereas if I plot the solutions in the yv plane, I plot position and velocity here, what do the solutions look like? Well, let's use this form. Y is cos t minus delta. What is v, which is y prime, is going to be derivative cosine is negative sine. I have minus r sine of t minus delta. So actually in the vy plane, I get v squared plus y squared is r squared using a trig identity. So the solutions in the yv plane, this is often called the phase plane, are going to be circles. No, they don't cross themselves. Okay. And they go around clockwise. One of the reasons you can see they go around clockwise is dy dt is v. So v is positive, y is an increasing function of t. And what I've drawn here is the trajectory in the yv plane of the solutions to y double prime equals minus y, or this system here. And the trajectories in the yv plane don't cross. Okay? What you have to pay to get that is that t is not visible here. We don't see t. The only remnant of t is the little arrows that say, well, as time goes on, the point moves around this circle. Okay, so we'll be getting back to this later. Later today, I'll show some videos of doing this with technology, but as far as today is concerned, in these problems, we really don't have to deal with all this. I'm going to get rid of this. This phase plane thing is important. We'll be getting back to it, in fact, even later in set 16 a bit, but for now, we're going to be just doing that very first thing we did. Okay, so let's do an example. Say like problem 6. Okay, suppose I've got a u double prime plus 3u prime plus 9u equals 5 cos of 3t. Okay, this I'm using u instead of y. U of t is position, but that's because the web problems use u instead of y. The textbook does as well, but a lot of the web problems in the past have used y. It doesn't matter. Hopefully you can be flexible about the name of the dependent variables. So this is a driven, damped mass on a spring. Okay, here's the mass, there's the spring constant 9. Okay, so what they want us to do is write this as a system of first order ODEs. We're going to let v of t be u prime of t, okay, be the velocity. Right? And let's just do it. So now we need to write the system of u prime equals something, v prime is something. Well, the first one is easy. U prime is v, okay? And I know that the equal sign is sort of symmetric. It's commutative, right? But usually, right here, we're defining V. Usually the thing on the left is what we're interested in, and the thing on the right is how to compute it. And here we're defining V as U prime. But here we're saying what is, we're writing U prime as something and V prime as something. That's the way we define this system, okay? And it's often tied together with this little curly bracket that you don't really need. But anyway, so this problem, U prime is V, is almost a giveaway. I know that sometimes the blank is quite long, and in web work you think that can't be that simple, but it is. U prime is V. Done. Move on. And what is V prime? Well, I got to solve this guy for U double prime. U double prime is minus 3U prime minus 9U plus 5 cos of 3t. So when I put it in the right-hand side, I can't use a U prime. I can't use a U prime in this system. I have to replace U prime by V, and I get minus 3V minus 9U plus 5 cos of 3t. Okay? All right. So this is an example of this fact in blue. Every second order single ODE can be written as a system of two first order ODEs. And the trick is just the first variable is U prime is V. And then, so I write in terms of U in V. U prime is V, then V prime is U double prime, right? But I have to write U double prime in terms of U and V. But I can always do that. Okay? So then the other thing is that this can now, given what we did before, that can be written as ddt of U and V. I can write this in vector form. I get this vector with components U and V. U prime is V, so that means that I can do matrix multiplication hope I have enough room here, right? If I get, so the first component is U prime or du dt, and that is U, 0 times U plus 1 times V. And then what do I have? The order is the opposite. Let's make order here. To do this, I got to put the minus 9 first, because it's minus 9 times U minus 3 times V, right? So that's how I get these two terms here is the second row, minus 9 times U minus 3 times V. And then I get the first U prime is V, that 0, 1 there. And then I have to add this part. Well, there's like a plus 0. I don't see it there, right? So then I have to add the vector 0 in the first component and 5 cos 3t in the second component. Okay, good. And if I had an initial condition, for a second order, the initial condition might be, say, U of 0 is 7, U prime of 0 is 3, right? That means the initial position is 7, initial velocity is 3. That gives me the initial conditions over here would be still U of 0 is 7. And instead of U prime of 0, it's just V of 0. The initial velocity is 3. Okay? All right, so this is very much like that problem 6. There's a one little wrinkle. I guess it's not really too much of one, but in problem 7, you're going to have some coefficient in front of U double prime. And if I have a coefficient in front of U double prime, I still have to solve for U double prime, and I do that by dividing everything through by that coefficient, right? If there was a 1 plus t squared in front of U double prime here, I just have to divide everything on both sides of the equation by 1 plus t squared, whatever that coefficient in front of U double prime is. So I can solve for U double prime. All right, so now finally I want to show you some of the phase portraits, they call them. Let's get to share the screen. All right, so I want to show you a little bit of this this app you've been using all through the semester. We've mostly been doing one ODE. Now we're moving to systems. So here's a system of two first-order ODEs, dx dt and dy dt. We're going to change the variables to v versus y. Right? So v versus y is a variable. So let's change the differential equation to the very first one we had. Okay, so this is a differential, oops, dy dt, sorry, is v, dv dt is minus y. This is if you go back to that first example, this is like y double prime plus y equals 0, or y double prime is minus y, right? So y double prime is v, and v prime, or the acceleration, is minus y. And you'll see that we get these little arrows swirling around. In fact, if I start with an initial condition, what did I predict? I had this picture where the solutions would lie on circles, right, in the v-y plane. Or the y-v, yeah, whatever. Oh, they don't lie on circles, okay? What's wrong? Well, do you trust me or do you trust the computer, the app? Well, don't answer that. Okay. The problem is that we're using Euler's method. And if you remember the scan I did from Hidden Figures, the scan was not Euler's method, it was for improved Euler's method. If I use improved Euler's method instead, it actually looks like it's going around in circles. In fact, all of these various methods, there's Runge-Kutta 4, that's sort of our go-to method. When you use Runge-Kutta 4, you see all of these solutions go around in circles. And they're actually moving through this phase plane in circles in the clockwise direction. If I had a different spring constant, maybe I could do, say, maybe 0.5. And then instead of going around circles, I go around ellipses. And you can get the parametric equations for the ellipse, which I won't go through, by finding the solution for y, and then finding, you have the solution for y and use that R delta form, and then you find y prime or v, and you can eliminate time to get equations for ellipses. Okay. All right. So we're going to be getting back to this, especially in the next set, 17. And we'll be also doing things like this. Suppose instead of this mass having a restorative force, y double prime, the acceleration, is negative y. Suppose a particle is sitting at the top of a hill. And if I move to the right, then the force is to the right. If I move to the left, the force is to the left. And their y double prime acceleration will be a positive constant times y. And that can happen, we can get that in something like this. dy dt is v. Okay, the derivative dv dt, the acceleration, or y double prime, is plus y. And then let's clear all these curves. And all right, so this is what the phase plane looks like. And if I start with 0 position, positive velocity, well, I'll just go moving to the right, okay? And if I start with positive position, 0 velocity, again, I start moving to the right, as we see in this thing. So this is what you get in the phase plane when this is the ODE for y double prime equals plus y, or y double prime minus y equals 0. And I get this. So we're going to be learning how to solve this equation without resorting to writing it as a second order single ODE first. All right. So I hope that you'll play with this app. You won't really need this for these problems 5 through 7. I'll be coming back to them with the rest of this set 16 though. So you might want to think about doing this, looking at this app. If not, you'll see it later. Okay, bye. Stay well, and let me know if you have any questions. Bye.